Hey everyone, today, you might have guessed, we're going to talk about the challenges of cross-platform development in Rust. Before we start, very short presentation. I'm Federico, software architect at Anima App, and throughout my career, I worked on multiple cross-platform applications, both professionally and as side projects. And one of them in particular, Espanso, is an open source cross-platform application that inspired this talk. So if you want to know more, I'm on Twitter, YouTube, and you can also visit espanso.org. Building software that runs on multiple platforms is hard. Every platform has its own frameworks, languages, best practices. And so the idea of re-implementing your software every time separately for each platform using the native technologies becomes really expensive, really fast. And so people have been tinkering for decades with the idea of building cross-platform application development frameworks. The idea of building the code once and then see it running across platforms thanks to the framework. Examples of such frameworks are Qt and WX widgets. You might have heard of them. And with them, you can write the application code once in C++ and then see it running across the many platforms they support. But in the past decade, companies wanted more. They wanted to build richer and richer user interfaces with animations, complex components, interactions, and the existing solutions proved to be challenging and limiting. And so, a bit of history. In 2013, some folks at GitHub were working on a text editor known as Atom. You might have heard of it. And they realized there was this key piece of technology that allowed you to create very rich user interfaces from a single code base, and then see them running across all the major platforms. You might have guessed it, I'm talking about the web. With the web, you can build rich UIs using HTML, CSS, and JavaScript, and then see them running across all the major platforms, thanks to web browsers. And so they started from this idea, and they created a framework. Electron. Raise your hand if you ever heard of Electron. So, quite a few of you. For completeness, Electron is a framework that lets you build cross-platform applications using web technologies. And the way it works is basically it bundles a Chromium runtime to render the UI and a Node.js runtime to interact with the system. And yeah, you might have noticed that nowadays Electron applications are everywhere, right? Most of the cross-platform applications nowadays are built in Electron. And the reason is cost. It's significantly cheaper to build cross-platform applications with Electron than the alternatives. For example, a company might have an existing web application, and with Electron, they can simply package it up as a desktop application that runs on most platforms. Moreover, they don't need to find developers experienced in desktop development. They can use the web developers they probably already have in-house. But despite the many advantages, Electron applications have some severe downsides. Due to the fact that they bundle an entire Chromium runtime, they are very resource intensive. And to be clear, as developers, we are lucky, because we run on the latest and greatest machines with fast processors, fast NVMe drives. And on those machines, the performance of Electron applications is decent. But as you move towards the lower-end devices, the performance and user experience really begins to suffer. And so, accepting the fact that probably, as a company, using Electron is likely the cheapest choice, what I would like to discuss with you today is a different perspective. What if cost was not our primary motivation, but rather performance, efficiency, and ultimately the end user experience, even on lower-end devices, was? So today we're going to talk about how to build performant cross-platform applications. And the first decision we need to make is what language to choose. There are so many languages nowadays. And so let's try to filter them out based on our needs. Firstly, we are building a cross-platform application. So we need to filter out all the languages that don't have an amazing cross-platform support. So, sorry, Swift, Objective-C. And then, and this will be controversial, because we are trying to build really performant and efficient applications, I'll need to remove from the list all the languages that are garbage collected. Not because you cannot build performant applications with them, but because they lack the level of control you need to make them really efficient. And these are some of the popular choices you have today if you want to build really performant software. But before going further, I would like to discuss the topic of memory safety. If you're used to working with a high-level language, you might have encountered a situation like this. In this very simple Python example, I do something stupid. I try to write outside of the list bounds. And the Python interpreter is really nice. It tells me exactly what the problem is, list assignment in X out of range, and it tells me exactly the location where I made the mistake. As a developer, that's amazing. I know exactly where to start looking to solve the problem. If I try to do the same in a language like C, you might encounter a segmentation fault. Now, raise your hand if you ever experienced a segmentation fault in your life. So a lot of you know the pain, yeah. Segmentation faults for a developer are not only much harder to, well, they are much harder than the exception we saw earlier because they don't give us much information. But they are not the worst that can happen if you use a low-level language. In fact, let's recap, as a reminder, what are segmentation faults. Segmentation faults are raised when your program tries to access a memory region that it wasn't supposed to access. In other words, your program did something really wrong. But what happens if your program does something wrong just a bit? In this other example, I initialize an array with 2 elements, and then a variable. Then in the middle, I do something stupid, again. I try to write outside of the array bounds. Finally, I print the value of the variable. Now, what do you think will happen if I try to execute this program? Will it crash? Will it print 5? Will it print 1? Well, the answer is that it depends. It depends on the compiler, on the operating system, on the compilation flags. We enter the land of undefined behavior, and that's a terrible place to be. It means hard to reproduce bugs, non-deterministic behaviors. We really don't want that. And so, getting back to our list, the only low-level language that is capable of preventing those bugs is Rust, thanks to its powerful memory model based on ownership. And so we go with Rust. To recap, why Rust? Great performance and efficiency, cross-platform support, memory safe, and we are going to get back to this in a second. It has an amazing foreign function interface support, which is a language interoperability feature. So now that we decided the language, we are ready to discuss the architecture of a cross-platform application. But first, let's briefly cover the difference between a web application and a native application. So web applications, by definition, run inside a sandbox, the browser. And that sandbox exposes a number of APIs that the application can use. And nowadays, I'm sure you know, web APIs can do crazy things. You can access MIDI devices. You can communicate with Bluetooth devices, crazy things. But you're still heavily constrained in the things you can do in a web application. You cannot do arbitrary network requests. You cannot access the full file system. On the other hand, native applications have pretty much full access to the system. You can access the full file system, arbitrary network requests, you can access the hardware. What I want to emphasize is that a key feature of native application is the need to access the system. And with this in mind, a typical architecture might look something like this. Very simple. We have a high-level business logic module. It controls the main functionality and behavior of your app. And then we have a low-level module which exposes some abstraction over the native functionality you want to do. And then we have the operating system. And the low-level module communicates with the operating system thanks to system calls and native APIs. The thing is, the lower level the operation you're trying to perform, the more platform-specific the API will be. For example, getting the list of running processes on Linux requires different APIs than on Windows and then on macOS. And so a typical cross-platform application might look more like this. We still have a high-level business logic module, still a low-level module that provides an abstraction over the native functionality, but then for each platform, we need to implement the specific functionality we want. And Rust is an amazing choice to implement such an architecture because we can use it for the high-level business logic modules, and then we can also interface it with the native APIs. On top of that, one thing to keep in mind is that each platform generally has a preferred language to do the low-level operations. On macOS, it's usually Objective-C. On Windows, it's C++. And so one thing you can do is to implement the native functionality in the best language for the platform, and then link it to the Rust module thanks to its foreign function interface support, which is, again, language interoperability feature. Okay, let's say that the functionality of our app is now ready. We need a way to present it to our users, to make it usable. And in Rust, there are a lot of libraries you can use nowadays, but really few are production ready. So let's try to discuss some of the viable approaches you might have today. If performance and efficiency and also system integration are your utmost priorities, you can go with the approach I call the shared library with native UIs. In a nutshell, you implement all the functionality you need for your app in Rust, and then you expose it as a shared module. Then, for each platform, you're going to implement a UI using the platform-specific APIs. The UI will then rely on the shared library to provide the functionality. And all of this is possible because in Rust, one thing you can do is package the code as a shared library that exposes a C API. Now, a C API is the golden standard of language interoperability. Pretty much every modern language can talk to a C API. And we're going to get back to this in a second. So to recap, why this approach has great system integration, great performance. I mean, you know how good native macOS utilities feel like, right? And with this approach, you get the same UX because you're using the same UI technologies. The downside, of course, is that it's quite expensive to maintain because you need to create and maintain multiple UI projects. And so a cheaper alternative might be to rely on a cross-platform framework to implement the UI, like Qt or WX widgets, and then use the same shared library approach. It's cheaper because you only have one project, but you get a worse system integration. We previously talked about the C API and how easy it is to use with Rust. So for context, just to show you how it's possible. So let's say that all the functionality of your app is in this Rust function, right? And we want to expose it. So how can you do it? You add some configuration to your Rust cargo toml, which is like the package.json of Rust. And then you add some keyword to the Rust function to basically tell the compiler to export it as a C API. And that's it. You compile it, and you get a library that you can then link and use from whatever language you want. And that's really powerful and makes Rust such an amazing choice to implement shared functionality between platforms. For completeness, there's also another framework that is getting very popular in the Rust space called Tauri. And the idea behind Tauri is very similar to Electron. You can build the application UIs using web technologies, but with one key difference compared to Electron. Instead of bundling the Chromium runtime within each application, which is typically heavy, Tauri applications rely on the system UI. So for example, Tauri applications on macOS will use WebKit to render the UI, the same web view powering Safari, and the same goes for Windows. In terms of advantages, you get huge storage saving, and it's still pretty effective in building rich UIs. But there's one downside, which is very significant. In Electron, one of the big simplifications you have is that you need to make sure that your front end works correctly on a single version of Chromium. That's it. Because that's the only thing that will ever render your UI. That's a huge simplification. With Tauri, you don't have this advantage. And so you need to make sure that your application works correctly on multiple browsers. And yes, including Safari, which I'm sure many web developers here know how painful it can be sometimes. So my suggestion here is, if you want to use Tauri, try to decouple your UI as much as possible from the Tauri APIs, so that later, if you see that the maintenance burden is too high, you can always switch to Electron later, and you won't lose most of your work. Packaging and distribution. We don't have much time, and these are some of the most complex topics in cross-platform applications. I like to think of packaging and distribution as the process of getting your software to work on our users' machines, starting from the source code. And there are so many challenges in this area, so let's try to focus on the interesting bits. Let's say we start with a simple Hello World Rust program, and we build it with Cargo. This produces a binary, this test Rust binary, okay? And if I try to execute it on my machine, it shows Hello World. So we made it work on our machine, but what we really care about is making it work on our users' machines, right? And so my question for you is, if I send them this binary file, will they be able to run it on their machines as is? In other words, if I place this binary file and I place it on their machines, will it run correctly? The answer, unfortunately, is a lot more complex. Firstly, one thing to keep in mind is that binaries are a collection of machine instructions. And each CPU architecture have a different set of instructions. So the basics is that if you want to support multiple architectures, you will need to ship multiple binaries for each architecture you're planning to support. But now we get into the really tricky territory. Let's say I compile the same Hello World program on a Ubuntu machine, okay? And as you can see, it prints Hello World correctly. But what if we copy that binary on a machine running Alpine Linux? I know, Alpine Linux is quite bad, but if I try to execute it, the shell tells me not found. And yet, the binary is there, and it's set as executable. What's happening? Well, it turns out that programs, even to execute the basic operations, require libraries. And in the context of native binaries, libraries can be used in two different ways, with dynamic linking and static linking. We don't have time to go into details, but in a nutshell, dynamic linking means instead of bundling the library code within the binary, we just add a reference to it. Then, when we execute the program, the operating system tries to load the library into memory and binds it to the binary. So the important bit is that the library code resides outside of the binary. With static linking, on the other hand, the library code is bundled within the binary itself. So the binary doesn't have an external dependency. And on Linux, there's this very handy tool called LDD. If you point it to a binary, it shows you the list of shared libraries this binary depends on. And if we point it to our Hello World Rust program, we discover two things. Firstly, that it depends on quite a few shared libraries, and so it uses dynamic linking, as we discussed. And most importantly, that those shared libraries are not there on Alpine. And so how do we solve this problem? We have multiple approaches. For example, we could try to find a way to bring those shared libraries into the Alpine machine. Or we could try with static linking, which means, reminder, to take the library code and bundle it within the binary itself. And so in Rust, if you're targeting Linux, you can do that by adding this configuration flag, which it's pronounced muscle. I know it's funny. And then yay, it works on Alpine. So keep in mind that static linking is not always possible or easy, but at least now you know that it's a possibility and you can read more if you're interested. Okay, we are officially out of time, so we covered just the tip of the iceberg. These are some of the topics you might be interested in reading if you like this space. And with that being said, thank you so much for listening.
Thank you very much, Federico. I'm sorry I was like laying, those 1 minute, 2 minutes and things like that for you. So please, on behalf of the community, accept this trophy and
Thank
gift.
you so much.
It was a pleasure having you here. Do you guys really believe it was his first time? Like, really? First time?
It was.
Definitely not the first time. But great guy. Round of applause for him. Great guy. Thank you for being here with us. So, let's collect questions. Lots of questions. Okay, this way. By the way, if you tag a picture or some kind of writing on LinkedIn with the hashtag OSDay2023, you're getting a t-shirt, or well, you might get a t-shirt. So go to LinkedIn, write stuff. Question.
Hi. Thank you for the talk. Just a question, like you presented different architectures for the UIs.
Yes.
But I didn't get what you prefer. So I think you're not that excited by Tauri, but maybe there's something else.
So that's a great question. It's the same as what language do you prefer? I see all these approaches as tools, and you should always choose the best tool for the job. What I can say is that my next application will use Tauri, but I'm not biased. I tried the other approach. I got burned once, and that's enough.
Great, thank you. Any other questions? I saw one. Go.
Hi.
Hi.
What do you think about WebAssembly? Like, can it be a choice on the talk you did?
So the main advantage of WebAssembly is that it provides this unified memory instruction set that we can run on so many different platforms, right? And in this particular context, there's not much point in using WebAssembly because with native and cross-platform applications, you can access the actual machine instructions. One place where WebAssembly could be very helpful is if you have some logic and you want your app to run both as a desktop app and as a web app. That could work. Or I also seen it for people wanted to create plugins in Rust, because, for example, creating a plugin in Rust would make it much harder without WebAssembly to run, because you will need to create multiple binaries for the architectures. Hope that answered your question, but if you have other questions, for all of you, you can find me on Twitter, and I'll be happy to answer and have a conversation about everything.